Welcome
Um,
again. Um, Thank you very much, Salman, for
mhm.
being with us. So, for the participants, it was really an honor to have you on board, Salman.
Thank
And
you.
actually, yeah, we really appreciate your efforts and your help. So, please, participants, enjoy learning with Salman. Go ahead.
Yep. Thank you so much, Kira, for inviting me for this particular. Uh, uh, so my strategy for this particular workshop is I'm not going to be using PowerPoints because I don't like them. I would be doing everything by hand and breaking down how exactly convolution networks work. So what is the mathematics behind it? Once we understand it, then you will see that making models, convolutional neural networks would be pretty easy. And if you have any questions while I'm going through every single thing, please feel free to ask me questions. Just raise your hand and I will stop talking and you can start asking questions. So feel free to stop me whenever you want. And if you don't understand anything, ask me questions, as many questions as you want. Okay. So I will start with simple basic thing. Now, so I would assume that, for example, some of you already know this stuff, some of you don't know this stuff. So I would be focusing on the people who don't know that stuff. Okay. So, which means my strategy would be to break it down based on the person who understands it the least amount. Okay, so that everybody is on the same page. If you understand it, that's good job. It's just a review for you. But if you don't understand it, feel free to ask me questions. First thing, which is the most important thing, is means I will not be breaking it down. I saw that previous workshops that you were attending, you have already been familiar with what is machine learning, what is deep learning, what is the differences and things like that. So I will not be breaking it down. I would be keeping everything specific to this particular kind of like short project that I would be doing with you, which is flower classification using convolutional neural networks and transfer learning. So first thing first, uh, machine learning, whenever we talk about it, technically, when we talk about machines, they don't see the way we do. So we can see different people. Our eyes can kind of like sense different colors, send the signal back to our brain, and then our brain processes it, and then it creates an image in our head. That's what happens in our brain, and that's what happens with our eyes. Machines, on the other hand, they do not understand images, they do not understand videos, text, or things like that. The only thing they understand are numbers. So, which means if you have an image, your goal is to convert that image into a number of certain form. And the best way to convert it is in a matrix form. So if any of you have taken linear algebra, you know that what are matrices. So matrices are simply a representation of several different numbers in rows and columns. That what we can say. For example, I can write 1, 2, 3, 4, which means these are the rows. I have two rows, and these are the two columns. So these are columns, and these are the rows. So these are matrices. Now, technically, what we can do is we can take a picture, and then we can assign a number to every pixel on the image, which means now when we assign a number, we are technically creating these matrices. Now, these matrices are just two-dimensional, which means they have a particular height and they have a particular width. But our images have colors as well. For example, red, blue, green, or so many different colors. In that scenario, we need a three-dimensional matrix. So in that scenario, so what we can say is matrices are technically two-dimensional tensors. This is what we say. So when we say they are two-dimensional tensors, what are tensors? Tensors are basically the representation of anything in terms of columns or rows or in these brackets like things. That is what we call tensors. Okay. Now matrices are tensors, and if I make a column vector looks something like this, which has just one column and multiple rows. This is a vector. It is also a tensor. And then if I want to write something like this, this is zero dimension, or you can say one means a zero dimension tensor, which means we can create 0 dimension, 1 dimension, 2 dimension, 3 dimension, 4 dimension, 5 dimension, so many different dimensions of tensors. So how we can create it means right now I will stick with 2 dimensions and 3 dimensions. That's it. I will not go deep down because that is a totally different topic, and we can cover tensors in detail. But right now my goal is to kind of like introduce a simple thing that machines only understand numbers. And anything that we are doing, for example, if I have a tabular data, for example, like I have 5 columns. So I have a diabetes data, for example, which is telling me that this is patient ID. Then I have the age of the patient. And then I have, after that, for example, what is the diabetes level of the patient? And then I have what is the family history of the patient, and so on. And I have some numbers over here. So I have number 101, and then I have age 26, let's say. Then I have a diabetes number, let's say 0.01 something milligrams per deciliter or something. And then family history is positive or negative. Maybe I would just say 1. So these are all numbers, which means if you already have the data, which is already in the number form, data pre-processing is very least amount of pre-processing you need to do. You just need to do data cleaning, and you're good to throw in that data into your machine learning model. But for image analysis, what you need to do is your images needs to be converted into a proper number, and then you need to do some processing on it, remove some noise, and you need to do some augmentation and things like that. And then it is ready to go into the machine learning model, and then machine learning model can learn from that. So let me give you an idea. For example, let's assume this particular box is a 1, 2, 3, 4, 5, 6. So this is a 6 by 6 box. This box is representing an image. All these numbers are telling the intensity of the color. So let's say the color black. Let's say this is a black and white image of something. I just created randomly. This is not a specific image. I just wanted to give you an example, and I just created this out of thin air from nowhere. So you can see that it has 1, 2, 3, 4, 5, total 6 columns. And then it has 1, 2, 3, 4, 5, 6 rows. That's why I'm calling it a 6 by 6 matrix or two-dimensional tensors. It has a width and it has a height. Now, if you imagine this is an image, which means you know that every single color means these numbers are representing the intensity of the color. 3 is less than 5, which means here this pixel is a bit darker than this one. Similarly, this pixel is a bit lighter than this one. This pixel is more darker than all of these on the left side. Then this one is less darker. This one is more darker than this one. So you get the idea that when I combine all these pixels in this particular manner, I will end up with an image at the end. And that is what happens. So when I throw in this particular box inside the machine, what machine is going to do? It's going to learn the pattern of these numbers. And based on those patterns, it determines that, oh, if this is the pattern, then it would be a face of an object. If this is, if the pattern is different, then it would be a flower. If the pattern is different, it would be an animal or something like that. So machine learns the patterns in the numbers that you kind of like give it to them by breaking down an image into a number form. So right now, I'm calling this input feature map. Now, if you know any idea, if you have any idea about deep neural networks, means if I start creating my dense layers, for example, let me give you an idea. A dense layer would look something like this. For example, if I would do TensorFlow dot keras dot layers, and then I would be doing a dense layer. So if I'm doing a dense layer, and if I make a fully connected neural network, and if I'm using a dense layer and I'm throwing in the image means I want to do image analysis or image classification, and I'm not using any specialized convolutional neural network. So what happens is basically it does not give a good result. It does not give a good result. People have tried it. And if you want, you can try it as well. I'm going to show you after I'm done talking about this theory. I will be showing you a code and I will tell you what things you can get rid of in order to try a simple dense version of the model instead of the convolutional. And you can see that the result you're going to get would be very poor. So that's where convolutional neural networks comes into play. What convolutional or how convolutional neural networks work, it's something like this. For example, if there is an artist, okay, so let's say I want to draw a person. So first thing I'm going to do is I'm going to draw the outline of the person, right? First thing I'm going to do is I will be drawing the outline of the person. Once I have drawn the outline, then I will draw the features on that particular person. Means whatever that person is, means I will start drawing the features. After I draw the features, then I will go and highlight the light details on the features. Means if there is a shade here, if there is a shade here, or what kind of shade was over here, then you would do the shading part and things like that. So when you are drawing a particular person or you are sketching a particular person, you start with the main outline, then you draw features or small features on top of it, and then you add a bit more smaller features or a bit more fine details onto it, and you keep on adding the fine details on top of it. Right? So this is a sequence happens. So first thing, what you do is you basically draw the outline. The second thing you do is you basically draw small features. Then you keep on further fine-tuning it. So when you keep on further fine-tuning it, what happens? So these things are happening, and eventually the picture starts getting clearer and clearer and clearer. Okay, so that is how a sketch artist can sketch a particular image. They start with the outline, then they start drawing some small features, then small features, then further fine-tuning, then further fine-tuning, and keep on doing that fine-tuning and adding different edges and things like that, and they get a good image at the end. Convolutional neural networks work exactly the same way. So when I am adding, let's say, 3 convolutional layers, the first layer would be capturing the main outline of the image. The second convolutional layer would be capturing some small details on top of. Means it's kind of like you look at a zoomed version of it. That would be the first convolutional layer. Then you zoom into the ears, for example. That would be the second convolutional layer. It would be capturing all the information about the ear. Then you zoom in further and see what are the edges of your ear and further detailed features of the ear or nose or eyes or something like that. So you kind of like keep on zooming into the image and keep on looking closely and closely and closely minute and fine features of the image. That is how convolutional neural network works. And the more convolutional layers you have, the more kind of like fine details you can capture. But keep one thing in mind, the more you must be thinking, If more convolutional layers can capture more fine details, then we should be using a lot of convolutional neural networks or convolutional layers? No, because model complexity keeps on getting bigger and bigger. Model keeps on getting complex and complex and complex, which means it will be increasing the technical depth, means the use of the processors and use of the cloud services. That's gonna cost something. So if you are using this in a company where they are paying for cloud services or things like that, it's gonna charge them really well. So you need to make a model which should use least number of resources. So you need to be very careful about it. Your model should be efficient and less, or you can say cheap as well. Okay, so these are the few details that we keep in mind when we are making models. Now let's understand how convolutional work, how convolutional capture these details. For that, let's come here. What happens is when I start defining a convolutional layer, so what happens is this is my image. So this is my image. What we do is I define a convolutional filter. It's your choice what size convolutional filter you want to define. What is a filter? It's just like an extensile. I know that when I was little, I had an extensile on which I can write an very classic A, and then I can write very classic B and C and D and things like that. Which means if I put it on a paper and roam around my pencil on that extensile, I can draw very good alphabets, and I can kind of like do very amazing calligraphy thing. So these filters are just like that. These numbers that you see over here, they are random numbers. So first thing, we in convolutional layer, what we do is we first of all define the size of the filter. Here, I'm using 1, 2, 3, 1, 2, 3. That means this is a 3 by 3 filter that I'm taking. Now, I need to randomly take some numbers inside it. This is just like the weights that we assign in neural networks. Initially, it is just random weights. But when the back propagation is working, these weights keeps on changing, keeps on updating as the back propagation algorithm is running. Okay, so in the beginning, these numbers are random. So I will take random numbers. Let's say 1, 0, 1, -1, -1, 0, 0, 1, 1, something like that. These are just random numbers because initially I'm just picking these numbers randomly. Now, how I can apply this filter onto this input feature on this image and extract the outline of the image. So what happens is we pick up this filter. So let me pick up. So let's say this is my filter. I pick up this filter and I simply put it on top of the left top part of this image. This is the left. So I pick this this particular filter and I put it over there. Now this filter is somewhere over here. Okay. Now what is happening over here? When I put this filter over here, element-wise multiplication happens. Okay. What is element-wise multiplication? Let me so element-wise multiplication. So let me show you what happens. So element-wise multiplication means this 1 is going to multiply with this 3. So 3 times 1, I'm going to get 3. Then -1 times 5, I'm going to get -5. Then 0 times 2, I'm going to get 0. Then 0 times 9, I'm going to get 0. -1 times 7, I'm going to get -7. 1 times 5, I'm going to get 5. And then 1 times 2, I'm going to get 2. And 0 times 0 is 0. And 1 times 6 is 6. So What I did is basically I picked the random filter and I applied on the top left part of it, of the image. And then I did element wise multiplication. Once I did the element wise multiplication, I ended up with this output feature map. What I'm going to do with this is I'm going to add all the numbers here. I'm going to add all the numbers here. So the numbers I'm getting is 3 minus 5 plus 0 plus 0 minus 7 plus 5 plus 2 plus 0 plus 6. So we can add it and we can see what number I'm going to get here. So what I can do is I can create another box here and I can fill it up. So let's create another box. Okay, and I'm gonna move this here. So I have another box here. So what happens here? Let me add it up because I just changed the number, so everything is changed, so I have to do it. So 3 minus 5 minus 7 plus 5 plus 2 plus 0 plus 6. So I ended up with 4, which means when I add all these numbers together, I ended up with 4. What happened over here is I'm going to write 4 over here. And that is what I'm going to call my output feature map. So technically it should be here. Now what I'm going to do is I'm going to move this filter 1 unit on the right of this image. So this filter, I applied it on the left side. Now I'm going to pick this filter all over again, and I'm going to apply it 1 unit on the right. And I'm going to repeat the whole procedure all over again. Let's repeat it. So when I repeat it, what's going to happen? I'm going to get some numbers here. So the first number I'm going to get would be 1 times 5 would be 5. Then negative 1 times 2 would be negative 2. Then 0 times 8 would be 0. Then 0 times 7 would be 0. Negative 1 times 5 would be negative 5. 1 times 4 would be 4. And 1 times 0 would be 0. And 0 times 6 would be 0. And 1 times 1 would be 0. And when I add all these numbers again, I'm going to get another number. And whatever the sum of this number is, I can see 5 minus 5 is 0. And 4 minus 2 is 2. And 2 plus 1 is 3. So I'm going to get 3. So I got the number here. Then you get the idea what exactly I would be doing next. I would be doing something like this. So now I'm going to move this particular filter on top of this section now. And I'm going to repeat the whole procedure. And I'm going to get another number down here, whatever number. For now, I'm not doing the whole thing. I'm just showing you what exactly is going to happen. And I think this box is going to be 1 unit bigger. So when I apply this, I'm going to get a number somewhere over here. Then similarly, what I can do is I can move this particular filter 1 unit on the right, and then I will get a number over here. And then I will move this filter 1 unit down, and I will keep on repeating. Means not 1 unit down, means 1 unit down means this 1 unit down. Then I will repeat it over here. And then I will move it on the right and keep it going on to the end. And then I will move 1 unit down and keep going to the right end. And then I will move 1 unit down and keep going until I'm done with getting the information from every part of the image. So let's say we ended up with a number over here. So I'm going to just write random numbers. I'm not doing every calculation, but you get the idea what the calculation is happening, right? Everybody is good. Anybody has any questions? How we are getting these numbers? Everyone's good? Anybody has any questions so far? Okay. So if you interact with me, that would be good, because you will learn if you ask question. If you're confused, you should be asking questions. And if even if you're good, at least saying that you're good would be good, or just raise a thumbs up. You can just press a thumbs up or something like that, or write something in the chat. Okay, so that I feel like I'm not talking to a screen right now. Okay, so I can see there are 27 people, so I got 2 responses, means I should be getting more responses. Okay, so yep, thank you. So now let's fill up all these numbers. I'm not gonna do all these numbers. I will just create a random numbers here. Okay, so these numbers that I'm creating, these are just random. These 2 are, I calculated them, but rest of the numbers, since it will take a lot of time, I will just put random numbers. Let's say this number ended up being -4, this number was -1, then this number ended up with 0, and this number is, let's say, 8, 4, 3, 2, 1, 2, 4, 5, 7, -8, -2, 3. Let's say we started doing that and we ended up with this. How do I know I will be getting a 4x4 matrix at the end? Because you can see that I started over here. This was giving me 1. That means out of these 9 numbers in the box, I was getting 1 number. Then I moved 1 unit on the right. And out of these 9 numbers, I got another number. And then I moved a bit on the right. And similarly, finally, I moved over here, which means I moved 4 times along the horizontal axis. Similarly, if you see, I will move 1 unit down. Then similarly, in terms of down, I would be moving 2 units down, and I would be moving. So you can see I will be getting 4 units or 4 numbers along the vertical axis, and I will be getting 4 numbers along the horizontal axis. So I started with a 6x6 matrix. I ended up with a 4x4 matrix when I applied the convolution in this particular manner. Now, this convolution, I am moving this box only 1 box to the left and 1 box to the down. So it will keep on moving 1 box, 1 box, 1 box now once it has extracted the information. But you can set this number, and in TensorFlow, excuse me, in TensorFlow, we can set that number by setting the stride length. Right now, our stride length is 1, but we can change the stride length over here. You can see that I'm repeating the information. For example, once I took the information over here, let me change the color. So once I took the information in this particular box, and when I moved to this particular box, 2 columns have been contributing to 2 different boxes here. For example, this 5, 7, and 0 is part of the box on the left, and it is also part of the box in the blue here, which means the information is getting repeated as well. And if you don't want it, so sometimes you can change the stride length maybe to 2, maybe to 3 or something. But for I always stick with 1. Okay, and I have seen majority of the people stick with 1 in terms of convolutional layer. So whenever convolutional neural networks you are making and you are adding a convolutional layer, what is happening inside the convolutional layer? This is what is happening. Now, another thing which is happening is you can set the stride length, you can set the size of the filter, you can set another thing. This is just one filter, but you can set how many filters you want. Not just one filter. You can use 64, 128, 100, 200, 300, 1000 filters. Those number of filters, which means this is a randomly generated numbers here. And I can create 1000 different filters like that. And I can apply those filters, and I can extract the convolutional or convolutional matrix out of it, which means the more convolutional, more filters I will use, more information I should be getting. Not really. So the first filter will extract majority of the information. Then the next one will be capturing less than the previous one. Then the next filter will capture less than the previous one. So you get the idea, which means more number of filters would not make your feature extraction process very efficient. As the number of feature keep on increasing, the value of the filters, or the means number of the filter kind of like does not bring extra value to the model. So that's why you need to make a model which should have the least number of filter size. Because when the back propagation is happening, when the training of the model is happening, these numbers is what the model needs to learn. So technically, these numbers gets updated while back propagation is working. So we start with random numbers, and as we do the back propagation, these numbers keeps on updating. The more number you have, the longer it will take for the training, and the more complex your model would be, and it will be more costly. So that's why we need to make a model in such a way so that we can use least number of these filters with best accuracy of the model. So that is usually the goal is whenever we are using convolution. Now, so far what we did is step number 1, we applied the convolutional layer. So convolutional layer, what it did is basically so convolutional layer, however many filters you will tell it to make, it will create those random filters, and it will keep on applying those filters and keep on extracting these output feature maps. Let's say if I have 64 of these filters, I would be getting 64 output feature maps. Now, what to do after that? What we do is we apply some non-linearity. So the next step, what happens is we apply some non-linearity, or you can also call it activation. You must have heard about the ReLU function. There are so many other LU function. There are sigmoid function. There are softmax function. There are so many different types of activation function. What this ReLU activation function does is basically now whenever you apply a ReLU function, what it does is basically any value, means wherever you're applying, if the value is negative or 0, it's gonna make the number 0. And if it is above 0, it's gonna keep it as it is. So this is my output feature, let's say from one of the filter of the convolutional layer, then it's gonna pass through the ReLU function. So when it passes through the ReLU function, we are gonna end up with something like this. Let me give you an idea. So it's gonna end up giving you something like this. So when we apply a ReLU function, this is gonna happen. So this 4, since it is above 0, this 4 would be as it is. This 3 is above 0, this 3 would be as it is. This -4 is below 0, this is going to become 0. That is what ReLU function does. This -1 is...
So sorry about that. Actually, I forgot to notice participants because I was really following you. Yeah.
Okay. Okay, yeah. So let's wait a few minutes so that everybody can join again. So anybody has any questions? Is everybody getting it, or it is going over the head, or I'm talking something that is totally different, or you were not expecting it? So do let me know so that I can change my pace or change my way or something.
Just I have a question.
Yeah, go ahead.
So one convolutional filter is equal to one convolutional layer, or one layer can have having many filters?
Yes, one layer can have as many filters as you can put. So when I'm going to show you the model, means for example, when we call the convolutional layer from TensorFlow, so we do something like this. From TensorFlow, we call it from Keras, and then we call the layers, and then we call the convolutional layer. So let's say I would do right now, don't worry about 2D or 1D. So what we do is we basically write the number of filters we need. So let's say I need 64 filters, which means it will create 64 random filters. I just gave you an example of one filter. So it can create 64 and you can change the number here, whatever you want. I'm writing 64, you can write 128, 32, just one, that would be fine. And so what are the parameters that you define? I will talk about it. The first one would be number of filters you want in layer number one. This is still layer number one. And in layer number one, you can have as many filters as you want. Then the second thing you define is the size of the filter. The one I described was 3 by 3. So I write 3,3 here. Then after that, you can write the stride length, means stride length can be 1. And after that, you can apply this activation function. So all these things happen in a sequence. And that is how I'm breaking it down, so that when we get to the code, you will understand the code really well, because everything is in exact same sequence in which I'm explaining it. Okay?
Excuse me, sir.
Yep.
Sir, is there any relation between sequences of layers and number of filters? Like first layer is
I will talk about it. Yes, there is.
And yes. Sir, is it possible to have zero filter with any layer?
Zero filter means then what is the point of adding the layer?
Yeah, that's
right.
Thank you, sir.
Yep, go ahead. Okay. So when I'm applying the ReLU activation function, you can see what ReLU does is basically it does not allow any number below 0 to pass through. Means if any number is below 0, it's going to make it 0. And anything which is above 0, it's going to pass it through as it is. So what happened is this particular convolutional output matrix turned out to be something like this, a bit different. So this -1, since it is less than 0, the ReLU function is going to make it 0. This 3 is greater than 0. This 3 would be as it is. This 4 would be greater than 0 as it is. 8 as it is. 0 would be as it is. Then 1, 2, 4, 5. Then 7 would be as it is. And this -8 would become 0. This -2 would become 0. And this 3 would become as it is. So what we did is when you write this line of code or this layer in TensorFlow, this layer ends up giving you something like this. So you start with an image, then it creates certain filters, and one of the filter is going to give you an output matrix like this, which will have means, for example, you can say the size over here was 6 by 6, right? But here I'm getting 4 by 4. So technically, if I say this is n by n, when I apply the convolutional filter of size 3 by 3, what I ended up with is I ended up with n minus 2 by n minus 2 matrix. So whenever you apply a convolutional matrix, this is going to happen. Now, this is where another parameter inside the convolutional layer comes into play, and we call it padding. So what is padding? Padding means you can see that over here, when I was applying this 3 by 3 filter, I was getting 4 by 4. If I want to get 6 by 6 as an output, means I want to keep this dimension exactly same. 6 by 6 input and output should be 6 by 6. Then what I can do is I can add padding. Padding means it's going to create another 2 rows, one at the bottom, one at the top, and 2 columns, one at the left and one at the right. with number zeros. So this padding means when I create this, now I will have a matrix, input matrix. Padding will convert my 6 by 6 matrix into 8 by 8 matrix. And then when I apply the convolutional, it's going to convert it to 6 by 6. So technically, I gave an input as a 6 by 6 and I got the output as a 6 by 6. So padding does that in this scenario. So when we are making these layers, keeping tab of the dimensions is very important, because majority of the time, a lot of people get stuck with the dimensions, because if the dimensions for the next input layer or the next layer in your model are not to the point, then your model is going to throw the error initially. And for some reason, the model is still working, then your model is not going to be efficient. Majority of the time, it's going to throw the error that the dimension does not match. And dimension is where a lot of people struggle with. And I will show you how to keep. Means right now I'm telling you that when we apply convolutional, it technically reduces the rows and columns n by 2. If your input is n by n, the output is going to be n minus 2 by n minus 2 if you do not apply padding. But if you apply padding, then it can be same. So if I set the parameter padding same, then what it's going to do is my 6 by 6 input image is going to get a 6 by 6 output convolutional matrix as an output. But if I don't do this same, the default one is valid. Valid means it's going to reduce 2 rows and 2 columns. Means 28 by 28 or 6 by 6 will give you 4 by 4. 4 by 4 is going to give you 2 by 2, and 8 by 8 is going to give you 6 by 6, and so on. Okay, so these parameters, you need to kind of like keep tab of it. Depending on your architecture, you need to change it. So this is the reason why these neural networks, scientists call them, or machine learning practitioner or deep learning practitioner, they call them architectures. This is just like buildings that you can create different structures, different architectures, different sizes, dimensions, and things like that. And if you know how you are changing the dimensions and how from one layer to the other layer dimensions are changing, that's where the architecture mindset comes into play. And that is where deep learning becomes complicated and more fun. Means it's kind of like an engineering. You need to engineer a new neural network model so that all the layers should be supporting each other. The model should not collapse and things like that. Okay. So far, what we did is we applied these things. Now, let's say padding. I use the padding to be the default one, which was, let's get rid of it so that you don't get confused. Now, what would be the next step? Convolution layers never go alone. They always have pooling layers along with it. What is pooling now? Let's talk about it. So what pooling does is, it's just like in machine learning, you have heard about dimensionality reduction, right? So PCA is one of the dimensionality reduction technique. You can do feature engineering, selection, or things like that to kind of like reduce the dimensions or somehow decrease the dimensions. And why we want to decrease the dimensions? Because model complexity. I don't want my model to take up a lot of computation power. So I want to reduce the dimension, and I don't want to lose the features that is extracting. I want to keep as much information as possible and try to kind of like make it less complex as possible. So for that purpose, if you come here and if you think about it all over again, since I have made a lot of mess, let me change a color. So you can see that when I was applying the filter on this particular box, I was using this column, and I was using this column, and I was using this column, right? Then I moved the filter a bit to the right. Let me change the color. So let's say now my filter has been moved to this position now. So if my filter has been moved here, you can see when I applied it on, when it moved 1 unit right, this column is still being used. This column is still being used, which means I'm using these columns multiple times, which means I'm getting the same information multiple times, which means if I can drop some numbers out of the numbers that I have got here, I would still have the information that I would not be dropping the key information, which means that information is getting repeated. So dropping some of the numbers would still keep the information intact. So what we can do is we can do the dimensionality reduction. So that dimensionality reduction in this manner, we call it pooling. So there are two different types of pooling. One is average pooling, and one is maximum pooling. What it means is, it's pretty easy. Let me explain. So just like convolutional layer, I was picking up the size of the convolutional filter. Pooling has a filter size as well. Let's say my pooling layer has, I will define my pooling size to be 2 by 2, which means now I'm picking up a box of 2 by 2 or a filter of 2 by 2. What this filter is doing, this filter, if I pick this particular green box and if I put it over here, what it's going to do is it's going to go here and it's going to pick the maximum pooling. It's going to pick the maximum number out of these 4. So what I'm going to do is first I will put this pooling filter on top of the leftmost part. And out of these 4, what is the biggest number? 4. So I will write, wait a minute. I will write 4 here. Then what I'm going to do is I'm going to move this filter, not one place. I'm going to move this filter 2 places to the right, which means here my stride length is 2, which means now I move to the 2 places to the right. And now if I'm applying the max pooling, this is going to pick up the biggest number out of these 4 and it's going to write it here. Since my stride length is 2, which means now I'm going to go down 2 places instead of 1 places. Previously, I was going 1 because stride length was left to right 1 and up to top to bottom 1. Here, since my stride length is 2, which means left to right, it will move 2 places every time. And if it's going down, it will move 2 places every time. So which means now it's going to go down. And now out of these 4 numbers, it's going to pick up the biggest number, which is 7. And it's going to write here. And then exactly the same thing. It's going to move 2 strides to the right. And out of these, the biggest number would be 5. I picked up 5. So when I apply the pooling layer, I reduce the dimension of my image, but I still kept the biggest or the most important information. Now, that is where the number of filters comes into play. You see, a 6 by 6 image ended up with a 2 by 2 image. So technically, this is a 2 by 2 image, right? Which means I reduced the dimension and extracted some key information from it. Now, since the size is getting reduced, I need so many filters so that means I get the features from every single corner of the image, not just the middle or something. Okay, so that is the reason why we need to have more than 1 filters when we are defining or defining these convolutional layers. So this pooling layer is going to do everything to every single filter, and it's going to bring it down to, in this scenario, 2 by 2. But depending on what was the input size, this size can vary. It doesn't have to be 2 by 2. It can be. Means if this one was not 4, it could have been bigger than that. If it was 6 by 6, it could have been 3 by 3, and so on. So convolutional layer always go hand in hand with the pooling layer. So one layer would be convolutional, then you will apply the ReLU activation, and then you will apply a pooling layer. And that combo is what we call a convolutional module. Which means one module makes up a complete combo. Now you want to add how many modules? It's up to you. So you can start with one, but one would extract the main features, just the outline. So at least 2 or 3 modules is usually ideal in convolutional neural networks. So the simplest one that you are going to see, so I will show you a simple one first, and then I will show you a complicated one as well. And you will see that the simple one would have at least 3 convolutional modules like that. And those convolutional modules are made up of 2 layers technically. One would be the convolutional layer, and the other one would be pooling layer. Now, pooling can be maximum or can be average. You understand what average is going to do. This average, if I was doing average, it's going to add all these numbers and divide it by 4. And whatever the number comes up with, it's going to put that number instead of the maximum number. So it's up to you. That is where hyperparameter tuning comes into play. If you're not able to improve your results or something like that, maybe just change the pooling type. Maybe from maximum pooling, you can convert it to average pooling. Maybe your results would improve or something like that. So that is where hyperparameter tuning comes into play. Okay. So this is a simple basic math of how convolutional neural networks work. So now, once I did that, I will repeat the same procedure on this. Since, for example purposes, I kept the size over here pretty small, but overall, usually I would be using maybe 28 by 28 image. Maybe I would be using 256 by 256 image, and I cannot make a 256 by 256 image and show you all those calculations on that. And then you can understand that your pooling layer is not going to give you just 2 by 2 matrix, so that it's going to give you a pretty big one, and you keep on reducing and keep on reducing it, so that you keep on extracting more and more and more features until you don't have, you cannot further divide it. Okay, so you keep on doing that. Now let me summarize the whole architecture or convolutional neural networks in steps. Any convolutional neural networks will always have a convolutional module, at least 3. So 1, then convolutional module 2, then convolutional module 3. Every convolutional module has 2 layers. One is the convolutional layer and the other one is pooling layer. Similarly, this one would have exactly the same thing. This one would have exactly the same thing. Now, when we are applying these convolutional, we are still getting the output of this one is a matrix, which means it would have some rows and some columns always. But the dense layers, they always take in vector as an input. What is a vector? A column vector means a column matrix is called the vector. It will always have just one column. So far, when I applied all these layers, you can see I'm still getting a 2 by 2 image. I don't need a 2 by 2 image. I need maybe 2 by 1 or 3 by 1 or whatever. I need one column only. I cannot have more than one column. So dense layers always take in, you can say, a vector column as an input, which means now since you are getting a matrix here, there is another layer you need to add, and we call it a flatten layer. So first you make a module number 1, then module number 2, module number 3 for the simple model. If you want to go extreme, you can add 10 different convolution module if you want. Then you need to add a flatten layer. What flatten layer does is basically, it does something like this. Let's say you have a matrix like this. Or maybe let's change the number. The flatten layer is going to do something like this, 2, 3. And then it's going to pick up this 4, 1, and it's going to put them down here. and it's going to make them flat. This is what flatten means. So when you add a flattened layer, you are technically reducing the dimension. So picking up all the columns and putting them or concatenating them. So concatenating them means one after the other. So so the first column is on its place. The second one would be below it. The third one would be below the other one, and the fourth one and the fifth one, and so on. So this is the input a dense layer usually takes, which means here I need to add a dense layer, but I could not because I need to flatten it. Now I can add dense layers. So these dense layers, now I can add multiple dense layers, not just one. So if you want just one, you can do that. But usually a fully connected dense layer is recommended, at least one of it. So this one can have maybe 32, 64, 128, or whatever number of neurons you want to put in. The more neurons you would put in, the more complex the model would be, the more weights it's gonna need to optimize, which means the more training time it's gonna take. So you need to keep that number as low as possible so that you can get as high accuracy as possible. So that is usually where the majority of the time in tuning or the models are spent. So when you add a dense layer, then you can add several different dense layers if you want. And finally, after the dense layer, you can add the final output layer, which would again be a dense layer. And this dense layer would have only the number of neurons. So how many neurons it's going to have? The number of outputs you're going to have. For example, if you are doing a binary classification, the number you would have just one, because you want whatever has the highest probability, whether it is a heads or whether it's a tail. If you are predicting the probability of getting a heads or tail, let's say, so you just need one answer, which means either a heads or tails, whichever has the highest probability, you want that answer. So that's why I would do that. But I would be doing a flower classification where I have 4 different flower classes, which means my number should be 4 here. So once I put 4 here, then I need to add an activation function. So all these dense layers have activation functions. So flattened layer does not have it, but dense layers do have it. So activation function. My output layer should have an activation function. For example, if this is a multi-class classification, I would be doing softmax majority of the time. But if it is a binary one, I would be doing simple logistic regression one, okay, sigmoid function, okay, and there are so many others out there, but right now I will keep. So softmax, by the name of it, you can understand what it's going to do. It's going to give the output of the highest probability. So it's going to give 4 outputs, and it's going to tell you what is the probability of every single class. And if you want to pick the highest class, that would be your answer. And you're going to see, means I'm going to show you how you can check that. Okay. So the output layer usually have the activation function this, but before that, any dense layers, fully connected dense layers, their activation function would majority of the time, you would start with ReLU function. ReLU is kind of like a standard one. You should start with ReLU, but for some reason, if that activation function is not you are not able to improve the results with this function, you can play with that. There are so many others. There is LU as well. There are so many. Okay, so right now just stick with ReLU because if I start talking about activation functions, there are so many of them. There is a complete lecture we can do just with the activation function. Right now, I'm not going to do that. Okay, so this is what we have, a theoretical part. Means this is how a convolutional. So the convolutional neural network architecture looks something like this. It has convolutional modules. Every module has a convolutional and a pooling layer. And then you have at least 3 convolutional modules. Then you need to flatten out the results of these convolutions. Then you need to throw in some fully connected dense layers, at least one of it, and then you need to add the output layer. And that is the simple, basic convolutional neural network architecture you can build. Now you can add and subtract and so many different things to it, but this is the simplest one. Sounds good? Anybody has any questions, any confusions? Please ask me. Then I'm going to move to the coding part. So I'm going to show you everything in working form. Anybody has any questions?
Not so far. No.
Okay. If no questions, then let's get to it. So I will be sharing these notebooks with you. And these notebooks are simple. So you can find the data set. So I did not use the data set. TensorFlow has some data set built onto its library. So this flower classification data set is already there. You can check out a tutorial. You can just search flower classification TensorFlow, and TensorFlow website has a complete classification tutorial. But I did not use that. I added my own stuff. So what I do is basically, I gathered my own images. So my data consists of 4 different classes, different flower types. We want to classify different types of flowers: dandelion, rose, sunflower, tulip. These are the 4 classes I'm taking. And I have several different images inside it. For example, you can see these are dandelions. These are different images. They are different sizes and things like that. Similarly, let me show you some of the other ones. So some of them random one. Okay, so this file is corrupted. So this one, you can see this one, you can see this one. These are all roses. And similarly, how I gathered this data, let me show you how to gather this data. So because majority of the time you get the data, and let me tell you one practical thing. Getting the data, cleaning the data is the most lengthy and most time-consuming part of any data work. So if you are in any data-related work, majority of the time, 80% of the time is spent collecting the data, cleaning the data, and processing the data. Making the models and optimizing the models is very small amount of it. Just maybe 5 to 10% of the whole complete process. 80% is the data gathering, cleaning, and pre-processing. So I would recommend you to practice gathering your own data. There are some web scraping methodologies and things like that. But what I did for this image classification, I used Google. So there is an Google Chrome extension. You can see over here. The name for this extension is Download All Images. Let me show you. So this is a Google Chrome extension, which I installed on my Google Chrome. Download all images. And once I downloaded it, I just displayed it over here. You can see this ZIP over here on my screen. This is the symbol for this download all images. Now, what this particular toolkit does, let me show you. What it does is basically, I will go on Google and I will search for roses, let's say. When I search for roses, I will go to images. Now I have images. Now I have a lot of images for rose, right? If I click this particular button on this particular page, what it's going to do is it's going to download all the rose images on this particular page shown, which means just with one click of the button. So I just clicked it. It is downloading. You can see the number is increasing. And then it's going to tell me where to save. Once it's done, it's going to ask me, can you see? I don't think. Let me share my screen. You can see now it is asking me where to save it. I can save it anywhere. Let's say I will save it over here. And once I save it, let's see how many images did we get. I got about 245. You can see this number over here. I got about 245 images with just one single click. So what I did is basically I gathered my own data. So I searched for rose, I searched for dandelion, I searched for sunflower, I searched for tulips. And I pulled out the images using this particular Google Chrome extension. Once I did that, I extracted them in my folder. Let me show you. So over here, you can see that this is my main folder. I created this data folder, and inside this data folder, I extracted all those zip folders over here. For dandelion, these are the images. For rose, these are the images. For sunflower, these are the images. And for tulip, these are the images. Now there's one thing. These images are of different types. For example, let me show you. Let me open up this. You can see this is JPG file. This one is a Microsoft Edge HTML. There are some other file types as well. JPEG file size as well. There are PNG file types as well. There are SVG file types as well. This is Microsoft Edge, right? My computer or my model is not gonna convert them into numbers, which means I need to delete them. So what did I do is I wrote a code. What it does is basically, so there is a library which I used. This is the library, imghdr, image H directory, so dr. What it does is basically, it looks for file extension types. So here I'm defining that these are the file types I want to keep. Anything other than that, delete it. So what I wrote is, I wrote a for loop that this for loop is taking. So this os.list directory is giving me all the folders inside my data folder, data directory. What is my data directory? This is my data folder. I'm inside the data folder here, which means this for loop is going to each individual folder these, and then it's gonna search for all the extensions which are not one of these. And if it is not one of these, it's going to delete that. And it will keep on doing that for every folder. So this particular code is doing all that. Once I do that, I will end up removing all the extensions which are not these four. I just want to keep these four extensions in my working directory right now. So once I did that, I kind of like run it, and you can see that I ended up with 694 total images. So let me run that again. So, okay. So do we have any images? So it is running, and it's going to clean up all the images that, or all the file extensions that I don't want. Which means now I have my own data. I don't need to get it from Kaggle. I don't need to get it from any other resources or things like that. I ended up means I gathered 694 of my images total. Now let's take a look at those images randomly. So some of the, what happened? Okay, so something is wrong with this. Why did it not delete it? So, okay, let's see. Let's run it again. It was working fine. So keep one thing in mind. When you are doing this Jupyter notebook, it usually saves these checkpoints, and you don't want those checkpoints inside there. So somewhere here, I have those checkpoints and I need to delete those. So IPYNB checkpoints. Okay, so let me open it here. Okay, just stick with me. This is part of troubleshooting. And I need these checkpoints. Okay, yes, these checkpoints, you need to delete these. These checkpoints are giving you the error. So let's delete that as well. And delete that as well. We don't have it. Okay, I think we are good now. Let's see if we can run it again. So if we run it again, we should have an image now. So we are not getting any error. That means, yep, see, it is working. Let's take a look at another image. We have this one. Maybe let's try number 10 as well. So you see, these are random images. So now I'm pulling out those images. That means my directories are working and everything is fine and things like that. Now, one important thing, TensorFlow allows you to create a data pipeline. What does that mean? So I have, let's say, 695 images or something, 865 or something images. Okay, so here it says 865 of 4 classes. What was that number then? Oh, these were just with this extension. So JPG files were this, but there were some PNG and BMP and everything. So we have total of 865 images. Now keep one thing in mind. If every single file is, let's say, 2 MB, 865 times 2, that many MBs is gonna create how many GBs of data? We know that 1000 MBs is 1 GB, right? So, okay, should we restart the session? I think the time is about to end.
Yes, yes. So we should reconnect again. Okay.
Okay. I think let's reconnect. Then I will continue.
Okay.
Okay. So what I was saying was that TensorFlow allows us to create a data pipeline. For example, if I have 865 images and every image is 2 MB, which means it's going to create about 1.6 GB of data. And just like in machine learning algorithms, if your data is too big, all that data, and if you are not making a pipeline, what's going to happen? All that data is going to sit inside your RAM. And if you don't have a big enough RAM, your computer is going to crash. So that is where TensorFlow gives you a data pipeline option, which means you don't need to put all the data inside the RAM of your computer. You can convert it into batches, and it's going to only pull out certain number of images in a batch, process them, train them, and then put them back, and then pull the next batch. Which means at one given time, if my batch size is 32, let's say, for example, over here, I'm defining my batch size to be 32. That means in one single step, my RAM is only taking care of 32 of the 865 images. So this kind of like is an efficient way to use your RAM and increase the training time and not the training time, improve the training time and things like that. So when the data keep on getting bigger and bigger and bigger, these data pipelines are going to help you. Right now, let's say, yes, my RAM is too big. Right now, 12 GB, which means I can throw in all the data. I don't need to make a data pipeline, but I can throw in all the data in my RAM and my computer will not crash for now. But what if I'm in a company and they have terabytes of data? Then I don't have that big a RAM, which means then I have no other option just to use this data pipeline. So we need to learn how to kind of like use those pipelines. So how to do that is, it's pretty easy. You see, what I did is basically I made a data folder, and inside the data folder, I made 4 classes and the folder for 4 classes. And inside every folder, the images are there. The data pipeline generator in TensorFlow, what it does is basically it goes to that particular specific folder, and whatever the name of the folder is, it will assume that is the label of that image inside that folder, which means this particular image dataset from directory thing, what it does is basically it goes to this data folder. Inside the data folder, there are 4 folders inside it. Every folder it will consider as one of the class. And then it will go to every single class inside it, and it's going to grab this image, and it's going to link this image to the folder name. And it's going to tell us that, oh, this image has a label dandelion. This image has a label roses. This image has a label sunflower, and so on. It's gonna do everything automatically. We don't have to do anything. What I did over here is I only decided or defined where my data is. Just told it that this is the folder containing all my data. Now it's gonna go into that folder and pull out all the information on its own. You don't have to do anything. Over here, I'm telling it that I need to divide it into validation set as well. So 20% would be validation set and 80% would be my training set. Then I'm labeling this particular subset as training set, which means this would be my training set. That means right now I'm taking that 80% of it. And then for validation, I'm going to do exactly the same thing. And I'm going to do validation, which means whatever I was not picking here, I would be picking here as validations. So it is exactly the same thing. What is this seed? Seed is basically random initialization, and we want to keep everything constant. That's why the random initialization seed number is same, 1, 2, 3, 1, 2, 3. This is a random number. You can pick any number you want, but as long as both the numbers here in training data set and validation data set are same, it should be fine. Then the next size is you need to define the size of the image. Size of the image is pretty crucial. We determined the size of the image somewhere where I think we did it later somewhere. Yes. So we did the size of the image somewhere here, 180 by 180. So did I do that? Yes, 180 by 180. You can see. So I determined it and then I put it here so that it doesn't change, because then these neural networks, these TensorFlow data pipelines, if the size of the input data is not right, it's going to keep on throwing the error. The adjusting the dimension is very crucial and very important. And sometimes this is the majority or bottleneck, you can say majority of the people get stuck here in understanding the dimensions when they need what dimension. Okay, so I created my training data set and I created my validation data set. Keep one thing in mind. These are not data set, which means if I print train_ds, it's not going to give me all the images, because this is just a TensorFlow data pipeline object, which means it doesn't have the images inside it. It's going to pull while training. If you want to pull all those things, you can use NumPy, iterator or things like that. But right now I'm not going to use it. So then what I can do is I printed out how many files I have, and out of those, how many I'm using for validation. And this many files, I'm using 692 for training. Now, class names, let's print out the class names. You can see it is automatically picking up the class names. I did not define anywhere. It is going inside and it is picking up the names of the folders automatically. Now let's visualize the data. So when I visualize the data randomly, some images with the labels, you can see these are tulips, 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 rose, dandelion, dandelion, tulips. So it's just random. So it is picking up randomly different images in a batch. Now, printing out these will help you, because if you would be asking me that why did I use 180 by 180, it's because I figured it out over here. This is telling me here that my image size is 180 by 180. What does number 3 means? 3 means it is a colored image. It has 3 channels, red, blue, and green. What this 32 means? This 32 means I'm picking out just 32 images per batch. So 32 is the batch size, 180 by 180 is the width and height of the image, and the number 3 is the 3 different colors, red, blue, and green. So technically, these are 4 dimensions over here. The first one is the batch size. The next 2 are the width and height of the image. And the third one is the channels, how many channels it has, red, blue, and green. For the gray image, this 3 would be 1. And you can see my target is just 32 things in batch. And this comma, nothing written here, which means it would be just it doesn't have any, you can say, dimensions, because my answer is just either it is a rose, it is a dandelion, sunflower, it is not an image. That's why it doesn't have any dimension. So over here, it is defined here. Next thing, what I'm doing is, so this is where caching and shuffling comes into play, and prefetching. Now, what happens is this data pipeline, it pulls 32 images and throw it into the model. Then model is going to do the back propagation and optimize the weights of that particular batch. While your processor is doing that, I can pull out another batch and pre-process it in the background, so that once my model has already optimized the training for first batch, I can right away, as soon as it is done, I can pull out the next batch, which is already ready for the processing part. So this prefetching and caching part is basically where I'm pulling out. So I'm keeping my pipeline active. Otherwise, what it's going to do is it will pull out one batch, do the processing, then throw it into the model, do the optimization, and then pull out the next one, and it will wait for the processing and then training. So I don't want to do that. If I want to make that process fast, what I can do is I can prefetch, which means while model is training one batch, the previous batch is already pre-processed and ready for the training. As soon as one batch is done, the other batch will come in and the next batch will pre-process. So prefetching makes the process a bit faster. So I kind of like define the prefetching over here so that I'm pulling out 2 batches. One is into the model and one is kind of like right now doing pre-processing. What is pre-processing? We'll talk about it. So pre-processing step, one of the step is standardizing the image. Means all those images are 256, means the numbers that we have in these images are in the range of 0 to 255, which means machine learning model, the bigger the number that you're going to throw in, the weights are going to be bigger and the computation power is going to be heavy. So the ideal thing is always normalize your data, keep it between 0 and 1. So that's where what I'm doing is there's a layer called rescaling layer. Just like the dense layer, convolutional layer, and pooling layer, there is a rescaling layer, which means you can add it inside your model. Over here, you can see this is my model, and I'm adding a rescaling layer. What it is doing is it is dividing every single value by 255, which means everything will be converted between 0 to 1, because the least value is 0, the highest value is 255. If everything is getting divided by 255, the biggest number is going to be 1, the smallest number is going to be 0, and everything will be in between. So now, deep learning models work really well if you have large enough data. If you don't have large enough data, that's where overfitting comes into play. Since I have only 865 images, and technically for training, I have 692 images, that is not enough data. How can I create more data? Now, if you have not seen, let me quickly show you. Okay, let me quickly show you what I'm talking about. Okay, so this is the image I created for my LinkedIn post. Let it open. Okay, you see the importance of data augmentation. This is a fun project I was doing. Exact same image, if you flip it vertically, it's going to throw in the garbage, which means it won't be able to recognize my face. Why is that? Because the convolutions and everything, they are sensitive to the variations in the space, which means if my face is in the middle of the picture, and in all the images, it is in the middle of the picture, and the testing set has my image on the right side of the screen, it will have hard time identifying it because it is remembering or memorizing the patterns that my image is in the middle. But if it is not in the middle, it's going to mess up. So data augmentation can take care of that. Data augmentation means it's kind of like cropping the data, rotating the data vertically upside down, horizontally left side right, or maybe shading it or cropping it or zooming it or things like that. So that is what we call data augmentation. So what I did over here is I just added few things just to introduce. I can add so many different things here. So over here, what I did is basically I did 3 different steps for data augmentation. I randomly flipped horizontally my image from left to right and right to left. I randomly flipped it, some of the images. Then I randomly rotated them 0.1 degrees on both sides. Okay. Then I randomly zoomed them into and out of them randomly, which means by applying these 3 augmentation techniques, all my images now have multiples of 3, which means 662, however many I had, 600 something, 692, about 700 times 3. Now I have 2100 images to train with, which means just applying 3 different transformations, I got 3 times the data. That means I can add more transformations and I can increase these data, and I can add a blur. I can increase the brightness. I can decrease the brightness. I can increase the sharpness. I can decrease the sharpness. So many different things I can do. I can crop the image. So all those things are going to keep on increasing the number of images. So data augmentation is a very, very good way to kind of like produce more data. Now, so I did that. After that, what I did is, I think I'm showing you the wrong thing. So after that, you can see, so this is rescaling. My bad. I think I was showing you something transfer learning, but let's keep the basic. So first thing what I did is basically I normalized my data. Right now, there's no data augmentation because I want to show you what are the results without augmentation, what are the results with augmentation. So here, no augmentation is being applied. You can see the first layer is the convolutional layer. And here I'm doing the padding, same. And here you can see the activation function is ReLU. Then I'm applying the maximum polling 2D with the normal default features. And normal default feature is a 2x2 filter with stride length of 2. So it's going to do 2x2. Then another layer of convolutional and then maximum polling. One thing to note about here, you see this number 16, 32, 64. Keep this in mind that you keep on increasing the number in powers of 2. You start with 16, the next one should be 30, the next one should be 64, the next one should be 128, next one should be 256, and you get the idea. Why is that? Let me show you. When you look over here, you can see that When I go from convolution to max pooling, this 180 becomes 90. And then this 90 becomes 445. If I don't increase that number, then this would be pretty much different and I would be losing a lot of information. So that's why I need to increase the number of filters every single time, or double the number of filters every single time, so that I can have as many features as I can. So that is the reason why we always start with the small number, then keep on increasing by in the power of 2. So this is 2 to the power 4, this is 2 to the power 5, this is 2 to the power 6. If I had another convolutional layer, I would be doing 2 to the power 7, 2 to the power 8, and so on. Then these are max pooling 2D. If you want to change them to average pooling, you can do that. Why these are 2D? You can see convolution is 2D because we are dealing with 2D images. If it was a video thing, then it would be, or time series thing, then it would be a 3D thing, because then you have a time dimension as well. So you can see that we have one module of convolution, we have second module of convolution, we have third module of convolution, then we have a flattened layer, and then we have a dense layer with activation ReLU, and then we have an output layer. And this output layer has a softmax activation function, which means this is exactly the same architecture I told you in terms of numbers. Now this is in terms of implementation. These are just these lines of code. That's it. Some of the lines are repetitive. So these 3 layers, you just copy paste them 3 times, just change this number. That's it. This 3 is telling you that the filter size is 3 by 3. And since the stride length is not defined, it is default, which is 1. Padding is defined here, same. If it was not defined, it would be default. It would not be same. Then you kind of like made your model. Now you have your model. What you can do is now you can compile. Compile requires 3 arguments. One is the optimizer. The back propagation is going to use a particular optimization function. Which optimization function it should use? Atom is a go-to one for majority of the problems as a standard one. You always start with Atom and then play with NADM or so many different others, RMS prop or SGD or so many different others. But always start with Atom. This is a good strategy because Atom is a universal one. Why Atom? Because there are so many different things happen, like vanishing gradient and those different things. If you don't know about it right now, don't worry about it. Just use Atom in the beginning. So then you need to define the loss function. So since in our scenario, we have multi-class, it is sparse categorical cross entropy. If it was a binary, I would have done binary cross entropy. So metric is what metric we are measuring. We are measuring the accuracy. It can be area under the curve. It can be ROC. It can be sensitivity, specificity, recall, or so many different things. But right now, I'm just using accuracy. Then look at the summary. This summary tells you the breakdown, how the dimensions of each individual layer changes. You can see the first one is this. Rescaling does not change the dimension, but convolution also does not do that. But max pooling reduce the size to half. Then convolution does not. If it was padding, it would have been reducing it. But then max pooling reduce it to half. Then it is same, then reduce it to half. And then we have a flattened layer. This number, you see this number? What this number is? You basically, how did you get this number? You multiply these 3 numbers and you're going to get this. 22 times 22 times 64 is what you're going to get. That means you have 22 rows, 22 columns, and 64 filters depth. And since I'm flattening it up, making one big column out of it, which means every single number should be the part of it, which means you can calculate it by 22 times 22 times 64 is going to give you this number. And then the next dense layer, you are giving 128 neurons as in, so this particular layer has 128 neurons, which are picking up these numbers. So then you have the final output layer 4, and number of parameters are basically calculated on every layer. And total number of parameters that we need to train while training the model is 3 million, 3.9 million technically, or 4 million, you can say on average. Now let's train it. When you train it, you can see I'm putting the training data set. I'm putting the validation data set for validation data so that I can look at the validation accuracy as well, and how many epochs I want it to run. For now, I'm just doing it 10. When I run it, you can see that this accuracy is the training accuracy. This is the validation accuracy. Look at these numbers. This one is keep on increasing. It reached 96%, but this one stayed at 80%. They started with very similar numbers, means you can see 0.68, 0.61, 0.73, 0.68, 0.74, 0.73. They were pretty close to each other. But then what happened? This accuracy kept on increasing, but this one did not kept on increasing. This is a clear sign and indication of overfitting the model, which means here our model is overfitting and it is maxing out at 0.82. You can say this is the maximum accuracy we are getting. But still there is a lot of overfitting here. Let's look at you can see until here it was pretty close, but now the difference between the validation accuracy and training accuracy is pretty big. And the losses are also pretty big, which means we don't want that. Once you see these kind of graph, these orange and blues getting separated, this is a clear sign of overfitting. Overfitting means the model has learned the data too well, but it is not doing really well on the unseen data, but it is doing really well on the seen data. So we don't want that. So that's where, so since our model was the basic one, let's see how we can improve. So when I do the testing and everything, you can see it is predicting, it is giving you these probabilities that the first label has a probability of 78%, which is dandelion. The second one a probability of 9.9%. The third one has a probability of 0.6%. The fourth one has a probability of 11.1%. And this one is a dandelion, which means it is still predicting right, but the probability is pretty not that high. How can we improve it? Improving it is one way, I have already told you, data augmentation. And the other way is using already trained models. We call them pre-trained models. And so right now I don't have enough data, right? So what these machine learning scientists have done is they have gathered a lot of data. And they have made very big models, very complicated models. And they have trained them to identify to an accuracy of 99%. Which means they have been trained on 1,000 different classes, on millions of data sets, on millions of images. Those models have been trained. So which means if I can get hand on that particular model and use it for extracting the features and add my own layers on top of it and apply it, I can get a good accuracy, right? I can improve the accuracy. And this particular thing is what we call transfer learning. So what you do is you basically grab a pre-trained model and add your own layers on top of it, modify it according to your specification, and use its learning to get your results or improve your results. That is what transfer learning is. So this particular notebook has exactly the same stuff what we did previously, exactly the same data, but here I'm adding two things: data augmentation, along with I'm adding, it's my VGG model. And along with that, I am pulling out a trained model. VGG16 is one of the pre-trained and the most less complicated model, you can say. There are less complicated than this. So 16 means it has 16 layers of convolution. So there is a VGG19 as well, which has 19 layers. Then there is AlexNet, there are ImageNet, there are MobileNet. There are so many different models out there. This one is a less complicated one, and if we print out the shape of it, we can take a look at it. For example, let's do that. So let's add VGG summary. right? You see this VGG model, it has 16 layers. The first one is the input. Then we have a convolutional layer. It has 2 convolution layer, then max pooling. Then again 2 convolution, then max pooling. Then again 3 convolution, then max pooling. Now that's where the architecture, I told you the basic version where you have a module of 1 convolution, 1 pool, but people have tried several different architectures, 2 convolutions and a pool, 3 convolutions and a pool, and so on, which means you can try these things. But in the beginning, keep things simple, at least 1 convolution, 1 pool you should start with. But if it does not give you good results, then keep on changing things and see if it improves the results or not. And that's what these amazing people did. So you can see that it has so many, about 16 layers, and I am blocking its training. You can see vgg.trainable is equals to false, which means I am telling it that I want all the learned material from it. I don't want, when I add this in my model, I don't want my model to retrain it because it is already being, so they have already some learned stuff. I don't want them to forget it and rerun it. So that's why I'm blocking, or you can say restricting them to train again. So I want to use their trained version of it. So that's why I'm blocking their training. And over here, adding the model is pretty much same. I'm adding the data augmentation part. Then I'm adding the rescaling part, just like previously, normalization. And then I'm adding the convolution layers. Here, my convolution layers are the transfer learning part, VGG model. And then after that, my model is exactly the same as the previous one. The last layers, I'm not picking the last layers of VGG. I'm just adding my own layers. And when I run it, when I train it based on everything same, you can see my results is going to improve. I had about 0.82 accuracy, and now my result increased to 0.89 or 89%. Technically, if you look at the highest number, it is 90%. That means I was able to improve my model with just small minor tweaks, nothing else. So with just few lines of code, I just improved my model. And this is what we call transfer learning, or you can also call it standing on the shoulders of the giants. Okay. If you look at the accuracy graph, these graphs are pretty good, close. They are still not ideal, but I can still tweak them and I can reduce it. Here, I added one more thing. Did you see this? This was not there previously. This dropout layer, what it does is basically, it drops out 20% of the neuron randomly during training, which means now my model is less complex and it reduces overfitting. So when I was not adding this dropout layer, my model was not that good. So what I did is basically I just added this dropout layer. By adding just one dropout layer, I improved my model comparatively because I was getting about 0.85. Now I have 90%, which means if I increase this number to 0.3 or 0.4 and try it again, maybe my model is gonna get better. So these are the things you keep on trying. When you make models, this is what you play with. Okay, and that's where your engineering brain comes into play, and that's where you're going to make your own architectures. These numbers, there is no hard and fast rule to get these numbers. Yes, we start with some basic ones, powers of 2, but you keep on changing them by improving. I mean, you need to improve your results. You keep on fluctuating them and changing them and see what happens, and based on that, just keep on changing if you want to improve your results. And finally, you compile the model, do that, and test it. You can see here we are testing. This one is not a good test. It is saying 50% it is dandelion, and 32% it is tulip. So it is still confused, which means for this particular image, it is not good. Let's see if it is doing good for another image. Maybe let's change the image. Let's take this one. I just copied these ones. So these are not part of the training image. They are just here. Let's see if this works for this one. Yep. So this one is saying 49%. It is this. 32% is this. There's some mistake here. Okay, you see this model is still not accurate. 90% accuracy means it is still not 100%, which means it is still throwing an error. But let's maybe check here what kind of results we are getting here. %78 is this. It is saying it is dandelion. So it is mixing things up, which means we still need to optimize it to improve the results and things like that. And we have an image data set on TensorFlow. I can pull out that it has about 3,200 images. I can add those images with my images, and I can improve the data set, and I can do data augmentation, because right now I just did 3 different transformational data. I can do 7 or 10 more. And then this way I will have so big data and my model is going to improve really well. Since this was a beginner workshop, I just wanted to keep things simple. And if anybody has any questions, feel free to ask. But that is what it is from my side for today. Anybody has any questions, please ask. Thank you so much.
So actually, So actually, just to say, what you have been doing is just amazing. Yeah.
Yep, thank you so much.
Yes, I'm pretty sure that dear questions, because this is an opportunity to learn. I mean, you won't have Salman every day, okay?
Yes, please feel free to ask questions if you have any. And feel free to connect with me on LinkedIn. If you have any questions, reach out to me on LinkedIn. I'm pretty active on LinkedIn.
Yes. Just to mention, just to mention, Salman, please, I shared with you yesterday our Slack channel. So please join us.
Yes, I've joined it. Yes, I've joined it. Yeah.
You can?
Yes, I have already joined.
And then, so participant, as usual, you have to use those notebooks and then try to modify and then to re-upload the notebooks. So please try at your end and then share with us your results. Okay?
Yeah. So I will upload these. I will give you my GitHub, and if you can give me access to the folder for this particular project, I can just put these notebooks over there, or maybe I'll just put it on my GitHub and everybody can access them.
Actually, I prefer to add you to give you the access. Yes.
Okay, sounds good. Sounds good.
To be part of our channel, yeah.
Sounds good. Yeah.
Thank you
I'm
very
glad
much.
that you guys enjoyed it. So, yep. So I think that's it for me. If everybody is good, then I'm gonna leave now. I have to get ready for my job.
Thank you very, very much. And just to mention, dear participants, it was 4 a.m. for Salman. So thank you very much for your efforts. It's really amazing. What are you doing here?
Yeah, thank you so much. Yep, everybody feel free to reach out to me if you have any questions or things like that. Yep, have a good one. Bye-bye.
Thank you. Thank you.
Thank you, sir.
Yep, have a good one.
Thanks a lot, sir.
Thank you.
Goodbye, participants.